let's get started. All right, so yeah, in the last lecture, we talked about conditional mutual information, and then, why is the change automatically? So, and then we talk about relative entropy, right? So let's see what we did. So basically, yeah, when we consider the conditional mutual information, so basically we need to consider three random variables, right? Here x, y, and z, and the distribution of them is given by this guy, right? So remember that it's still a PMF distribution, right? We're still considering the discrete random variables, okay? And so this is the definition of the conditional self-mutual information, right? The only difference here is that we know z, right? So condition is on z, given z, okay? And if we write their definition, then we can, and then take the expectation, then we can get the conditional mutual information is given by this formula, right? So here the important thing here is that, so the average is on all the random variables, okay? So yeah, this is very important, and so most of the information theoretic concepts, they're like average thing, okay? All right, and then we introduce the concept of relative entropy or the KL divergence, right? We start from talking about what? The cross entropy, right? So what is the total number of bits, or what is the code length we need to encode some random variable when we only have an estimate of the distribution of this random variable, right? And then we say, okay, from there we can introduce you the relative entropy, right? So basically, yeah, the relative entropy is given by this, right? So one meaning of relative entropy is how many more bits you need to encode a source message when you only have an estimate of its distribution. Q, right? How many more bits you need, right? So that's yeah, that's like, the origin of relative entropy, right? So, but later on you're going to see that, so we're going to use some other interpretation of relative entropy as well, right? But here, so yeah, it's important to remember the meaning of it, right? So if you know that, then you may not want to, or you may think again when you want to use this as a distance metric, right? So that is not a distance between two probability measure. Okay, it's not a distance. However, so it is related to the distance actually, right? So by the way, so what is a meaningful distance to measure two probability distributions? Right, either like this kind of definition, right? If I have a distribution P, and we have another distribution Q, right? And then, how can we determine the similarity between those? Yes?
Could you look at that intersection? Like if you have the one distribution and the other distribution, see where they overlap?
Not really. So normally that is not what we're looking at. Never thought in that way. Yeah, probably we should we should think, the overlapped area. Oh, maybe we do. Yeah, maybe. Yeah, maybe we do. Maybe we do. Yeah. Yeah, I think you're right. Right. So basically, any other different opinions? I think that makes sense. Very nice. Yes.
Look at the difference, like subtract them.
Exactly. So I think that is pretty much almost, I think, the same as what you said, right? So the overlapped area basically mean, if we look at the opposite of it, it's like the difference between those two, right? Yeah, that's right. So basically, we just, compute the difference between the, element-wise difference and then add them together, absolute value. Okay, so that is called total variational distance. Okay, it turns out that the total variational distance and this guy, so they're related. Okay, and that is called, if I remember correctly, that's called Pinsker inequality, right? But my point is that, okay, so this is not the distance metric, but it is indeed related to some distance metric actually, okay? And so one direct application of relative entropy is that, so if we compute the relative entropy between px and y, and px times py, right? So px is the marginal distribution of pxy, right? And the same for py. So if we compute that, it will give you the mutual information. Okay? So it basically means that mutual information is a special case of relative entropy, right? But for mutual information, if you switch x and y, it will give you the same thing. Okay. All right, and these are a list of the property of relative entropy. The first one is not commutative, right? And then second is that, okay, it's sort of distance, but actually it's not, because, so first of all, it's not commutative, and second of all, we do not have the triangle inequality, right? So as we mentioned in our class. And the third one is that if Q is 0 and P is bigger than 0, then relative entropy could be infinity, okay? And lastly, so we can show that this guy is bigger than or equal to 0, okay? And so when the equality holds when P and Q are the same, okay? So this is an if and only if condition, right? And then it can imply that the mutual information is also bigger than or equal to 0, okay? And we did prove that in class, right? How do you remember how did we prove it? So what's the key step to prove it? Yes?
We looked at like the growth of one function, and then we compared it to like where it meets the other function x minus 1, and then we showed that one was strictly less than the other one.
Yeah, exactly, right? So we compare basically log n and 1 minus x, log x and 1 minus x minus 1, sorry, right? So that's one way to prove it, right? Later on, probably we're not going to see that today, but we're going to see that on Friday. So we can use another approach to prove that. Okay, so that can be more like general or more meaningful, I guess. All right, so this is where we were in the last class. Okay, so today, today's our lecture number 7. Yes. Okay, so today, so we're going to continue talking about relative entropy. So we still have a little bit left. Entropy, spelled it wrong. And then, so yeah, I wrote it a few times already. So we'll talk more on the chain rule. And more on mutual information. Okay, and let's see whether we can finish those two topics or not. So that's our goal. And if we have time, or in the next lecture, so from the next lecture, probably we're going to spend a few more lectures on this. So I'm going to introduce you 4 most important inequalities that we're going to use in the future a lot. Okay, so we're going to talk about 4 important inequalities. Okay, so just to tell you which 4 that is here, right? So if you're interested, you can look ahead. Okay, so the first one is Jensen's inequality. Right, who heard of it? Yeah, what is that about? Yeah, very good.
Output average is bigger or
Yeah.
equal to the average of the inputs.
Yeah, exactly. So it's the average of the function and the function of average, see which one is bigger. Okay, yeah, so basically this is when we consider whether a function is a convex or concave. Okay, so who knows what is convex or concave? Okay, yeah, I'll introduce you. I'll talk about that. So yeah, let's see how detailed we want to do that. And second one is probably, yeah, very few of you may heard of. It's called log sum inequality. Log sum. Okay, this is a very specific inequality. So in most of information theory class, we introduced that. But based on my memory, so we almost never use it. So we use it maybe like 1 or 2 times when we prove something very specific. But yeah, we did use that. Yeah, maybe 2 or 3 times. Okay, but it is pretty important. Yeah, there are important results. Okay, the third one is extremely important. So that's the data processing inequality. So this, inequality. So basically, this is to measure, So yeah, when you have a Markov chain, right, or when you process the data, okay, then when you measure the mutual information, then we're gonna see, okay, if the data processing help you to increase your mutual information or decrease your mutual information, okay. So that's pretty interesting, and we're going to use that a lot. And lastly, so this is probably the most important inequality here, besides the first one, Jensen's inequality. It's called finals inequality. Who heard of that? Okay, great. Yeah, so yeah, that's extremely important, right? So we're going to talk about that in very detail. And after all of this, then we should be ready to talk about the Shannon's first theorem, which is a source coding theorem, okay? But we're going to spend a few lectures on this. Okay. Okay, so let's see the first topic here. Okay, so yeah, let's see how we can start it. Yeah, maybe I'll just repeat one thing here, right? So for the mutual information, okay, as we just see, so we can understand that as the relative entropy between px and y and px, py, right? And we know this is bigger than 0. Okay, so that's another way to see the mutual information 0, and the equality holds if and only if when pxy equals to px times py. Okay, or this basically means that the random variable x and the random variable y are independent. Okay, so this means that they're statistically independent, then the mutual information is 0, right? So as we mentioned in the very last part of the class, right? So when mutual information equal to 0, then they have to be independent, right? But when the mutual information is not 0, it doesn't mean that they're less dependent. Okay, and so one important thing to note here is that this is if and only if, right? I think from here, if I give you the fact that pxy equal to px times py, then you can compute it to see mutual information is 0, right? That's easy to see, right? But the other way around is not easy. Okay, so we're going to prove that using one of the inequalities that we introduced later. Okay, and another thing here is that so if we consider conditional mutual information, so that equals to this minus this, right? And then that will be bigger than 0, okay? And so that's exactly the same as before, right? So the equality will hold if and only, if and only if pxy given z equals to pxz times pyz. Okay, so I think there's nothing surprising here. Okay, let me ask you one thing, okay? So why we want to consider the conditional mutual information separate? Right, as we kind of said that before, so the conditional, when we consider anything conditional, right, so things becomes very weird, okay? So if you know z, so can you think, so whether the value of the conditional mutual information is bigger or less than just mutual information between x and y, right? In other words, so this and that, so which one is bigger? Or depends? Yes?
I think the first one would be bigger.
The first one, why?
Because assuming there's not independence, then we know something.
Assuming what?
There's not independence.
It's not independent
Means that the mutual information is not zero.
okay. Mm-hmm.
So I would think it would be bigger now that we have more information because we are given Z.
Mm-hmm. Remember the meaning of mutual information, right? It's the uncertainty reduction, sorry, right? But what you said makes sense, okay? But or at least it can make sense, right? But will that make sense in general? Any different opinions?
So like the left side would just be greater unless they are independent, then they would be equal.
Oh yeah, yeah, they are independent. Of course, they are both zero, right? But let's say they're not zero. Right, so one way to think a little bit on this is that, it can be easily write, so this equal to this, right? And this equal to, for example, this, okay? And we know this guy is smaller than or equal to this guy, and this guy is smaller than or equal to this guy, right? Therefore, the difference, normally, it kind of depends, right? So we're going to see, So the answer of this question is that, so this guy could be bigger than that, and it could be less than that. It really depends on the relation between x and y. Okay, so you may think about that now. So we're going to go back to this problem later, right? But yeah, this is one important property of mutual information, right? So it's not the same as entropy, right? Conditional entropy is always less than entropy, right? But conditional mutual information may not. All right, before going to that, we need to introduce you some other concept. So yeah, we talk about conditional entropy, we talk about conditional mutual information, and we talk about relative entropy, right? So what's left is conditional relative entropy, right? So we're going to talk about that. Conditional relative entropy. Or we call that conditional divergence. Conditional divergence. Okay, so one direct way to define that is given by this, right? So we want to consider relative entropy between Px and y, and Px given y and Qx given y. Okay, and so by definition, right? So basically, what we get here is that. So sorry, should be in x. We sum over x, Px given y, log Px given y over Qx given y. Okay, so if I don't specify the base on log, you could assume it's either 2 or e. Okay, so that's most commonly used. Okay, right? So yeah, the reason I use this notation, I think it's just a direct. Right, if you consider a conditional distribution, so naturally we should use this kind of notation, right? But if you look at the book, I think it's slightly different. Okay, so don't get confused, right? This is my notation, or the very conventional notation. Okay, but in the book it's a little bit different. So, but that is not the conditional relative entropy, right? So now I'm going to introduce you what is the conditional relative entropy, right? So why it is not conditional relative entropy? Right, just directly, we can directly borrow, the relative entropy concept from before to write this formula, right? But what's the catch here is that it's a y, right? So normally when we define information theoretic concept, so we want to average on whatever you have, right? So basically, the definition of the conditional relative entropy is this guy, and then we do expectation over y. Does that make sense? Okay, so let's write it down. So now, given given x and y following distribution, px and y, and then the conditional relative entropy of px given y and the qx given y with respect to py is given by d pxy and qxy given py, right? So that equals to the expectation of this guy, right? Then we do the average over py, right? And then we copy whatever here. Okay, so we put that here. Okay, and then so we can combine again. So we have a py here, we have a px given y here, right? We can combine them using Bayes' rule. So we have a sum of over x and y, px and y, and then log px given y over q x given y. No, sorry, yeah, x given y. Right, does that make sense? Okay, I think in the book they didn't write this here probably, but you know what I mean. Okay, I think it's more clear in this way. Right, so any questions? The meaning of that is still the same, right? It's like if we know y, and then, you know, what is the relative entropy between, you know, these two distributions if we know y. Right, the meaning, there's no big difference, okay? Questions? All right, okay, then let's talk about second topic. So this is more on chain rule and more on mutual information. Okay, so yeah, now we introduce you the chain rule on entropy, and did we introduce you the chain rule on mutual information? Probably not yet, right? So we only know the chain rule on entropy, right? So now let's introduce the chain rule on relative entropy, okay? Chain rule for relative entropy. So basically now, yeah, let's try to derive it, okay? So when we talk about chain rule, then it means that we must at least have two random variables, okay? So now we consider a distribution, x and y, follow a distribution like px and y. And then let's consider the relative entropy between this and the qxy. Okay, so let's derive it to see, you know, so basically the chain rule basically means that here, okay, so I have x and y, right? So we want to, you know, create a term of the relative entropy between px and qx, and then add another term related to y, something like that. Okay, so again, so that's from the Bayes rule, right? So let's do that. So basically, if we write down the definition, so this is what we got, px and y log px and y over qx and y, right? As we said, right, so if we want to create a relative entropy between px and the qx, then we need to take the px out and the qx out, right, using the Bayes rule, right? So basically, what we got here is that, so we have pxy here, and then inside log, so we take px out, right, and then we have p y given x, and here we have take qx out, we have q y given x. Okay, and clearly, so because of log, then we can break it from here, right? Make a plus. So then for the first term, this is what we got. This way looks right. Okay, pxy log pxqx, and add py given x over qy given x. Right, I think now it's pretty clear, right? So the first term, that's basically the definition of the relative entropy between P and Q. Okay, X. So that's the relative entropy between Px and Qx, right? And then the second one, yeah, I forgot, I need to add a term here. So we'll have a Px and y. Okay, and the second term, so that's the definition of the conditional relative entropy, right? So that's basically equals to d p y given x, q y given x, given. So be careful here. So given now is x, right? So given px. Okay, so from this, we can know that this guy equal to this plus this. Okay, so this is a chain rule for relative entropy. Okay. Okay. Yeah, any questions? Good. Okay, so if we know the chain rule of relative entropy, so let's see some application of it. Okay, so first let's see application of the conditional divergence or the conditional relative entropy. Okay, so now let's see whether we can write mutual information as a conditional divergence or conditional relative entropy. Yeah, I use conditional divergence here, just it's shorter to write. Okay, same thing. Okay, so now let's try to derive it. So yeah, let's write down the definition of mutual information. So this is given by this. Right, so this is the definition of mutual information, right? So now we know that, so for this guy, we can write that as px and times py given x, right? So this is the base rule, right? And from here, we can see that this px can be canceled, right? And what is left, or another definition of mutual information, is given by this, right? Px given y divided by py, okay? So if you see this, right, and compare it to our definition for conditional entropy, conditional relative entropy, you can see that it's almost identical except this term, right? So here's q here, right? Pxy, px given y, here's q, and if you compare with the definition of entropy, definition of mutual information, so we can see that, so this guy is the same, right? Of course, it's x given y, right? So it doesn't matter. And here is the, it's py, okay? In order to write it as,
Should be py given x, right?
py given, oh yeah, wait. Yeah, sorry. Yeah, it should be py given x. Yeah, we can write the other way around, but downstairs has to be changed as well, right? So py given x, then they're the same, right? So see, yeah. Oh, here I write x given y, but yeah, here's y given x, but the format is the same, right? So in order to write that as a conditional mutual information, right? So we may imagine, so this guy downstairs, so that as a q y given x, right? But this is a very particular qy given x, so that's equal to py, right? So then, if we think in that way, we can write this as the conditional relative entropy between p and the qy given x, where qy given x is nothing but py, and then given px. Right? Okay, so yeah, let's try to understand this, right? Since we can write that in terms of the relative entropy, then what's the meaning of it? Right, first of all, so if it's given x, then it means that by observing x, and then we see, okay, what is the amount of mismatch between py given x and py? Right, that makes sense? So this is kind of another understanding of mutual information. Okay, so yeah, this is one way to write mutual information as the conditional relative entropy. Okay, so another thing that may be very useful, especially in statistics or when we prove, and also in machine learning. So there's another important way to write mutual information, right? Which is to write mutual information as the difference between relative entropies. Okay, let's see how we can do that. Mutual information as the difference of divergence. Okay, so this basically means that we want to write the entropy as the difference between two divergences, right? So now let's consider again, so x, y, so that follow this distribution, right? So, and we consider, so here we consider qy, so this is another distribution, right? So this to be another marginal distribution or PMF of y, for y. Okay? So qy just, it could be an estimate of y or whatever, right? So that's basically, it's another distribution, another marginal distribution of y, okay? So now, given that, so we can write mutual information as following, okay? Here, so what we're going to do is that inside before we have py given x divided by py, right? So now let's use qy as an intermediate step, right? So what we're going to do is that we do this. So we use py given x divided by qy, and then times qy divided by py. Okay, we just divided by qy and multiply the qy back. Okay, and then we separate these two. Okay, then so this becomes py given x over qy, right? And then so minus, so we take the py on top here. Okay. So you'll see why we're going to do that, right? So, and from here, so we can basically see that. So first let's see, so what is the first one? Right, so this is the same as this guy, right? almost same, right? So here is a QY instead of PY, right? So the first one, so this is nothing but the conditional KL divergence or the conditional divergence given X. Okay, so now let's see what is the second one, right? So let's see what is this guy. So again, so here, if we sum this guy, so all of them is function of y, right? So if we sum this over x, then it will marginalize it, right? So we're not going to have any x anymore. So basically, the second guy will become this guy, log py over qy, right? So marginalized over x. Okay, and what is this guy? Right, so that's another KL divergence, right? That's just the KL divergence between py and the qy. Okay, so now we can see that mutual information also equals to the difference between these two divergences. Any questions? Let's see the meaning of it, right? So here, so by introducing a QY, so QY could be something related to PY, right? Could be estimate of PY or so, right? So basically, it means that, okay, so what is the mismatch deduction if we observe PX, if we observe X, right? So this guy is a mismatch when we observe X, right? And then this is a mismatch without observing X, okay? Then what is the mismatch detection? So that will give you the mutual information. Does that make sense? Somehow? Yeah, this is pretty confusing, right? So yeah, when we use it, it probably becomes more clear. But I think this is just a way to write mutual information, in terms of the relative entropy. Okay, and it just will have different applications. Okay, so I'll introduce you now. When we apply that, I'll repeat it. Okay. Questions? Yes.
I don't understand the step where you marginalize on x and you reduce the summation over x. Could you explain that, please?
Oh, no problem. Yeah, I think maybe I'll use another. Yeah, you mean from here to here?
Yeah.
Yeah. So this is again a Bayes rule, right? For example, let's say. Let's do this. So. Yeah, let's say if I have a x and y here, right? So if I sum this over, let's say, what did I do here? Sum over x, right? So if I sum over this over x, right? So that equals to what? Use again Bayes rule. So this is px given y times py, right? Okay, so we can take this py out, right? So that's now related to x. Okay, and then we sum over this, right? So this is the probability distribution, right? If we sum over all the possible x value, then that equals to what? 1. Exactly. Right, then that equals to py. Yeah. Very good. Okay. Other questions? Okay, you can see that we use a lot of this Bayes rule, right? So, okay, so next let's see the chain rule on mutual information, right? We see a chain rule on relative entropy. The next thing is chain rule on mutual information. So chain rule is extremely useful when we prove some information theoretic inequalities. Okay, so this is extremely important. So yeah, we'll consider chain rule again. So now we'll consider general version of the chain rule. So we have a lot of random variables here. So basically, we assume that we have a vector of x, right, denoted by x power n, right? This means that we have n of x, and we have a y here. So the distribution of this is this guy. Oh, it's late. P, x, n, and y, so that's the joint distribution, right? We have n plus 1 random variables, okay? So this is x1, x2, up to x2 up to xn here, right? So now the chain rule is given by the following, okay? So basically, let's see. Yeah, I'll use a new page probably. So if we consider a mutual information between x, n, and y, right? So that is going to be what? So that going to be given you by x1, y, plus I, x2, y given x1, plus I, x3, and y given x1, x2, plus and so on, right? So the general term, the last term would be xn, y given x1 till xn minus 1, right? And in short, we can write down this as this guy, and the y given xi minus 1. Okay, so that's the chain rule for mutual information, right? How to prove that?
Grouping property.
Oh yeah, I mean, definitely. You can, yeah, because everything is proved from that, right? So you can, but yeah, you can do something much easier here, right? So remember so of course, you can use I think the property, the chain rule of relative entropy. I think that may work, okay? But there's an easier way to do it, right? Now, so besides the relative entropy, right, the other thing we know for the chain rule is entropy, right? So we can basically use that property, right? Do you still remember chain rule for entropy? Right, so this h, x, n, so that equals to what? Summation over I from 1 to n, then we have xi given xi minus 1, right? So this is a chain rule for entropy, right? And we know the mutual information, right? So that equals to this, right? And then we can use the chain rule for entropy for each of them, right? So for the first guy, we have this, right? And then for the second guy, we have almost the same thing, but we have a y here, okay? And then we just combine them, right? So we have a sum over n h xi given x minus 1 minus h xi given xi minus 1 and y, right? And from here we can see that, so this guy is nothing but the mutual information between xi and y given xi minus 1, right? And then we finish the proof, right? So here's the proof. Right? Yeah, pretty straightforward. Okay, so yeah, let's see what's the next thing. Okay, let's see how much time. Oh, not so bad. Okay, so yeah, next thing, so we're going to go back to the problem I introduced in the beginning of the class, right? Let's see how far we can go. Okay, so we're going to talk about conditioning, okay? So we know that the mutual information, so that equals to this guy, and equal to this guy, right? And we know it is bigger than or equal to 0. Therefore, we know that this guy is bigger than or equal to this guy, and this guy is bigger than or equal to this guy. Okay, so it basically means that conditioning reduces entropy. Okay, so but the same thing will not hold for mutual information. Okay, so the conclusion is that, however, no general inequality relationship between conditional mutual information okay. Okay, no general relationship basically means that, either of them can be bigger. Okay, so now we're going to consider some special cases. Okay, so we may consider, the special case one. So we're going to consider a case where the condition can increase the mutual information. So can you think intuitively how come this can happen? Right, we consider 3 random variables. Okay, so remember the meaning of mutual information is that by observing y, so how much uncertainty of x can be resolved. Okay, so now in addition to observing x, and then we can see another random variable. So in this case, so we can resolve more uncertainty. So what that case should be, right? Meaning that, if we know z, it is really helpful. It can help you to gain more information. Can you think a case? No, not at all. Right? Think about this, right? The mutual information, x, y, is equal to this, for example, right? And also, no, not also, and this guy equal to this, right? Oh, given z, sorry. Given z minus this, right? And in order to gain, so want to see a case where this is bigger than that, right? And we know there's a clear relationship here, right? For this guy, we know if condition will reduce entropy, right? So we know this guy is bigger than that, right? But the first one is also reduced. Then we don't know which one is bigger, right? But what if the first one is not reduced? Then the bottom will be bigger than the top. That makes sense, right? So this guy is bigger than that. But if this and that are equal, then we're fine. When that'll be equal?
If x and z are independent.
Exactly, right? So x and z. Independent. Then it means that conditions can gain mutual information, right? Intuitively, does that make sense? is almost, I mean, this formula basically tells you the intuition, right? So, if z is something independent with x, but it's not independent with y, right? But observe, by knowing z, you basically can resolve more information. Okay, so yeah, so let's write it more accurately. So in this case, we consider this distribution would be like px given py zx z given x, py given x and z, right? So in this case, so basically we consider p, x, and z are independent, right? So that will be the case. Okay, and in this case, we can conclude that this guy is bigger than or equal to this guy. Okay, so yeah, I think that will be it for today. So we're going to consider another case where the mutual information would be, so this would be bigger than the following. You can consider what kind of situation that would be. Okay? Great. Yeah, thank you.